look at some main pipe welding defects, but this can also apply to plate welding, actually any kind of welding. And this is really just a short class on some of the basics and the most critical type of pipe welding defects. Any of you that go on and take welding inspection technology, you're going to get this again, but much more thoroughly, and we're going to cover a lot more than the 4 or 5 items that are covered here. Weld and base metal discontinuities. Well, a discontinuity, what's a discontinuity? Any interruption in the uniform nature of an item. That's a discontinuity. When we're talking about welding, if you have slag in your weld, that's an interruption of that weld metal. Okay, so that becomes a discontinuity. A defect. A defect is a non-conforming discontinuity. Well, what's that mean? It means that that discontinuity exceeds allowable, acceptable limits. So every defect is a discontinuity, but not every discontinuity is a defect. Because you can have a discontinuity, an interruption of the weld metal, but if it's small enough, if it's within code, it's acceptable. So some discontinuities are acceptable, but no defects are acceptable. So, discontinuity criticality. How critical are they? Linear and nonlinear. Well, linear means straight line. Okay? If it's a line, it's really critical if it's a line, like a crack. That's a line. The end condition. Is the end of that line circular or is it sharp? The surface condition. Is it on the surface or is it underneath the surface of the weld? Again, that relates directly to how critical that defect is. Is it in a loading, uniform, or non-uniform situation? Fatigue or impact. So is it going to be exposed to something where it's going to have uniform loading on it, meaning it's exposed to uniform stress over the entire length, so that's uniformity. But if it's non-uniform, if there's more stress applied to one part of that discontinuity than the other part. Well, if it's linear, it's really critical. And if the end condition is sharp, and we're going to be talking about cracks here, the possibility is that crack is going to spread. And cracks, well, I've got some little stickers that say cracks kill. They really do. Well, here's something that you might not associate with cracks. Arc strikes. What's an arc strike? An arc strike is a discontinuity resulting from an arc consisting of any localized remelted metal, heat-affected metal, or change in the surface profile of any metal object. Well, that's a long-winded way of saying you've dragged that arc, your stick rod, across the surface of the parent metal. Every time you do, and it's making those sparks, you're leaving arc strike. Sometimes they're called chicken scratches. Well, you think, no big deal. But if you take a look at this is a photomicrograph of a martensite structure produced by an arc strike. That's one of those arc strikes blown up and magnified. And I don't have my pointer with me, but if you look, you can see little tiny cracks spider webbing out of that arc strike. You can't see them with the naked eye generally, but every time you drag that arc across that metal, you're leaving these little tiny microfissures. And they're linear, they've got sharp end conditions, and they spread. What's a crack? A crack is a fracture-type discontinuity characterized by a sharp tip and high ratio of length to width to opening displacement. So there's all kinds of cracks. There's toe cracks, there's throat cracks, there's transverse cracks, there's linear cracks. Your textbook, I'm going to read from your textbook real quick. Arc strike cracking. Reading from the second paragraph under that subject, it says, when the arc is removed and it is very rapidly cooled again, in effect it is quenched. This affects on a relatively small volume of metal, the remainder not being heated appreciably. What they're talking about is when you strike that arc across there, you've heated that base metal right there where that arc strike has been struck, but nowhere else. And because you've struck it right there, you've changed the structure of that steel. You heated it right there, but nowhere else, so it wasn't uniformly heated. And that can cause that metal structure to change to a martensite structure, which results in your cracks. It says, as explained in Chapter 11, when the carbon content in steel is high enough, heating it to above the critical temperature and quenching it results in the formation of martensite. Low carbon martensite can even form in low carbon steel if the quench is drastic enough. With the addition of alloying elements, martensite will form at a lower carbon content and at a slower rate. The martensite forms while the metal is cooling at some temperature below 700 degrees Fahrenheit, and metal that has formed into martensite expands. This expansion of the metal results in internal stresses that may cause small micro cracks to occur on or just below the surface. That's what we were seeing there, micro cracks. If the arc is struck in the area over which the bead is to be deposited, the metal that is stressed or possibly cracked is melted a short time later as the bead is deposited, which eliminates the problem. So if you strike in front of wherever you're going to weld, drop back, pick up your puddle, and then weld on over it, and you're going to remove any of those cracking. But if you strike outside the joint and then move into where you want to weld, you're going to leave all those arc strikes and all those little micro fissures in there. And incidentally, if you happen to do that while you're welding to the 1104 API 1104 code, that's going to be a cutout because it's not allowed. And you're going to get about 2 cutouts before they're going to run you off because they won't keep you on if you're sloppy like that. Arc strikes are sloppy. If cracks resulting from the arc strike appear on the surface, a weld bead must be deposited over them. The bead should be made reasonably long and wide in order to increase the amount of heat input to the defective area, thereby reducing the cooling rate. Of course, the cardinal rule to follow is never to strike the arc outside the weld joint. That's the main thing. Just keep everything right in the joint. So this is the definition of a crack. And as I said, there's all kinds of cracks. Hot cracks, cold cracks, delayed cracks, underbead cracks, longitudinal, transverse, throat, toe, root. Has is, of course, heat affected zone. And so that would be a base metal crack. And there's many more. These are all different types of cracks that you guys may come across, especially if you're working in alloy steels. Anything that has a high carbon content or carbon equivalency over 2.5 is subject to cracking. This is a crater crack in aluminum, and it's kind of hard to see, but there's a crack right down in the middle of that, and it was caused by the guy just breaking the arc too quick. And the result was it propagated all the way around this tube. You can see that crack, and it's one of those little tiny cracks that we saw in that first picture, and it was just left to grow, and it grew all the way around there and broke the entire thing out. And that's what crater cracks can do, either from terminating the arc too quickly, or by dragging the arc across the surface metal. Now, on page 208, your book talks about underbead cracking. This is an example of underbead cracking. Let me get a pointer here. Now, you can see this is a T-joint. And it's cracked right in here where they had a lack of fusion. But right here, it's also cracked. And the reason it cracked here, well, it could be 2 reasons, actually. This is right in the base where the base metal hits the parent metal. If it's really restrained and you do a lot of welding in there, as it shrinks, it could crack and pull away. This one here, if you can see real closely, the weld metal stops right in here. And you can see the crack running outside the weld metal. So this is in the heat affected zone. This is where you have deposited the weld, but the adjoining metal, where it's a little dark out in here, this is the heat affected zone where the metal structure was changed by the heat of welding, but it didn't melt. You got it hot enough to change the structure, but not hot enough to melt it. That's the heat affected zone. And you can see that it's pulled and cracked right along in the heat affected zone. Now your textbook says, underbead cracks. This form of cracking occur within the base metal at a very short distance away from the fusion line. The fusion line is where the weld metal meets the parent metal. It occurs in low alloy and high alloy steels. The factors responsible for this form of cracking are not as yet completely understood. It is known that dissolved hydrogen gas must be present. However, otherwise underbead cracking does not occur. It is believed to be caused by stresses within the metal that are the result of the unequal contraction of the base metal and the weld metal, the restraint of the cooler base metal, stresses caused by the expansion of the metal when martensite is formed, or stresses set up by the precipitation of hydrogen out of the metal to form molecular hydrogen. That's a mouthful. But basically, what molecular hydrogen is, when you're welding, there's all kinds of forms of hydrogen around. There's a hydrogen in the air, there's hydrogen in your breath, there's hydrogen in any moisture. If you have grease or oil or anything on your gloves, there's hydrogen in the petroleum products from that. Hydrogen can get dissolved into the weld metal. So what happens is this hydrogen forms molecules, and it nestles between the grain boundaries of the base metal. And if you don't allow it to precipitate out, that is, if you don't post-weld heat treat it and allow it to precipitate out, just like the bubbles if you open a can of pop, how it fizzes out, hydrogen will do the same thing, but on such a small scale you can't really see it. So you've got to allow it to post-weld heat treat enough to allow that hydrogen to precipitate out of the weld. If you don't, it forms hydrogen molecules which nestle between the grain boundaries, and then those grain boundaries put pressure on the base metal and it causes it to crack. That's underbead or hydrogen cracking. Underbead cracking, it's often delayed. You can finish a weld, walk away from it, and think, boy, that's pretty, and come back the next day, and it'll be cracked. That's particularly true in certain types of steel. It's caused by hydrogen. It's difficult to detect, and you can avoid it using the low hydrogen process. You're using low hydrogen electrodes like 7018, but to stay within the code on using low hydrogen electrodes, you've got to make sure that they've been heat stabilized. You take them out of the rod of them, you use them. You don't leave them exposed to the air for more than 6 hours, well actually for more than 4 hours, depending on the moisture, atmospheric moisture and so forth. So you've got to maintain that quality control. Let me read from your book again here. I'm on page 209. It says, the presence of hydrogen seems to act as a trigger to start the formation of these cracks. Since the presence of hydrogen is the primary cause of underbead cracking, everything possible should be done to prevent hydrogen from entering the molten metal. Not only will it cause underbead cracking, but much more commonly, and the thing you can see with that, is porosity. Hydrogen in the weld metal will cause porosity. So if you're seeing porosity, there's a good chance that you could possibly get underbead cracking from hydrogen. One thing about hydrogen and underbead cracking, though, is it's usually got to be a heavy weld for you to have underbead cracking. Small stuff like 3/8 of an inch or so, that's not real common. But if you get into heavy weldment, an inch thick or something like that, then you can get underbead cracking. It says the primary source of hydrogen in welding is moisture. Well, moisture is one. You don't want to use wet electrodes or an electrode that's been exposed to the atmosphere too long. I do an awful lot of welding inspection, and I had a guy tell me one time, this was an authorized inspector. An authorized inspector is a guy that's authorized by the state or an insurance agency to come out and inspect on a job to make sure everything's being done correctly. And I, as just a regular inspector, he has authority over me. He's the guy that has the final say, because money's involved, of course, and safety. And he told me one day that he can tell how tight a job is by the rod control on the job. If he walks through a job and he sees some 7018s laying in a bucket out someplace and some guy's using it, that's bad quality control of the rod. That's bad control. Because how long has that rod been out? How long has it been exposed? When you're out on a job like that and you're welding to code, you have to have a little portable rod oven with you. And you keep your electrodes in that rod oven, and you keep that rod oven plugged in. Often a lot of guys will check out a rod oven, but they'll get someplace that they get lazy, they don't want to drag an extension cord or something, and they'll have a rod oven, but it won't be plugged in. So when I see that, I make what they call a bouquet, a flower bouquet. I'll open up that rod oven and I'll break every stick of rod that they've got in there, and I'll just leave it bent, laying in his rod oven, and they'll come back and they'll see it and they know that I've been there, and I've been called some pretty unpleasant things for doing that sort of thing, but it sends a message. They know that they were wrong for doing that because they violated the code. So, again, reading from your book, it says, if the weld metal cools more slowly, some of the hydrogen gas that has been dissolved will have an opportunity to escape from the weld by precipitating out. That's what I was talking about. If you post-weld heat treat it, or you can throw a blanket over it, or you can take a rosebud and warm it up, let it cool off slowly, then it can have a chance to precipitate out. But if it cools quickly, then it's going to get trapped in there and it's going to exert that pressure. Okay, we're going to go to undercut in a second. That's the next thing on the item. But reading from your book one more time, I want to talk about restraint cracking. This is on page 209. It says, because restraint cracking, what's that imply to you? Anybody? It's been restrained in some manner, correct? Okay. So you're welding two pieces of plate together, and they're part of a wall, and you're making that weld in there. Well, they're held rigidly in place. We're talking about, plate welding right now. So there's no give. Well, if you're welding in there, the shrinkage forces of welding is going to cause that to draw in. And if it was allowed to give, then distortion, that if those plates were allowed to give and distort, that would help to eliminate that restraint cracking. If they aren't, those stresses are going to be built up in there. You've got to relieve those stresses someplace, somehow, or else it's going to continue to crack. So, reading from your book here, it says, because the parent or base metal is much cooler than the weld metal, solidification progresses from the fusion line inward. For this reason, the center of the weld is at a higher temperature than the remainder of the weld while it cools. The mechanism of restraint cracking can be illustrated again by resorting to an imaginary situation as seen in figure 13.2. Basically, let me draw a picture here. Let's say you have a weld like this, and let's say it's 1 inch thick. Okay. Well, that's quite a bit of metal. So you fill that baby up. Well, what happens to the weld metal when it's cooling? It cools from the cold parent metal in towards the center of the weld, and that's what our textbook says. So it's cooling out here, but it's still hot in here. So you have a disproportion, a non-uniform type of cooling. Well, when that happens, the stresses are building up out in here. And if you look at figure 13.2 in your textbook, it's on page 210. What happens when you have this ununiform cooling, it's going to solidify here, and it puts stresses here, and it can crack right down the center, which would be a throat crack. So you want to try to make sure you've got uniform cooling on this thing. And if you can't, then what are you going to do to relieve it? Well, you can post-weld heat treat it. And of course, anything that is 1 inch thick or more has to be preheated. You should preheat it and then post-weld heat treat it if the carbon content is too high. And the code says that for something that's 1 inch thick, you're going to post-weld heat treat it for 2 hours at approximately 1100 degrees per inch. And then after that, it would be 15 minutes per each subsequent inch. So if this was 3 inches thick, we'd actually have to post-weld heat treat it for 2.5 hours to relieve the stresses, allow that hydrogen to precipitate out, allow those stresses to relax. So there's two different types of cracking that we're talking about so far. Underbead cracking and restraint cracking, because we haven't allowed the stresses from welding, the expansion and contraction during the welding process, to allow those stresses to relax in there. Two different types. So on page 211 in your text, it says, a thick weld having a larger volume of metal will accommodate more deformation without cracking than will a thin weld. Therefore, as shown in figure 12E, which is part of the figure on page 210, a heavy weld is less likely to crack than a small weld when they are on thick metal sections. Okay, that's two types of cracking. Now I want to go ahead and talk about undercutting. And this is the second discontinuity that we're going to talk about. Undercutting, of course, it's going to occur if you're making T-joint welds, if you're making plate welds, if you're making pipe welds. It's defined as a groove melted into these base metal, into the base metal adjacent to the weld toe or weld root and left unfilled by the weld metal. Here's some examples of it. Here we see a T-joint, and we've got undercut right here. This is real common in the horizontal position if you're not using the correct rod angle. On plate, again, if you're not using the correct rod angle here, you can get undercutting, particularly on the upper side of the root bead. So correct rod angle is paramount to avoiding that type of undercutting. Undercut adjacent to a fillet weld. So you can see the shadow cast right here where it's been undercut. And what happens when they undercut? Okay, does anybody know why that's bad? That's exactly right. And any of the codes you're going to work to are going to tell you that your weld metal has to be at least as thick as the parent metal. And so if you leave it undercut like that, the weld metal is now not as thick as the parent metal. But even worse than that, this undercut creates what we call a stress riser. If this weld was subjected to vibration, it's hooked up to a diesel engine somewhere out in the oil field here, okay? And that diesel engine's constantly vibrating. It's sending that vibration through this metal. And when it's passing through here, the vibration can simply move right on through. But when it hits here, it's like an ocean wave breaking against a break wall. It's going to continually slam it. Boom, 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 repeatedly slam it. And that's where the stresses are going to build up, and this is where it's going to crack at. Oh, I love my blackboard. Okay, next slide. This is a picture, a radiograph, an X-ray, of surface undercut. It's kind of hard to see, but the arrows are pointing to it right here. It's a darker edge along the edge of the toe of the weld. But notice, surface undercut should be found with VT, visual inspection, not RT, not radiographic inspection. Those of you that go on and take welding inspection technology are going to get a big dose of visual inspection and what to look for. So reading from your textbook then, undercutting. When the base metal along the edge of the weld is reduced from its original thickness, as shown in figure 13.3, the weld is said to be undercut. There are several reasons why undercutting occurs. Excessive current can cause the edge of the joint to melt, and the molten metal will wash into the weld, leaving a drain-like impression at the edges of the weld. This can occur in varying degrees, even with a normal arc length. Undercutting can occur if the electrode is not manipulated in such a manner as to supply an adequate amount of filler metal to the molten edge of the weld. Technique's big. If you're running too hot, using too long an arc length, moving too fast, all of those things can contribute to undercutting. On page 212, it gives us some reasons. It says excessive welding current, incorrect electrode manipulation, using an incorrect welding rod which provides filler metal of the wrong composition. You could be using the wrong type of rod. Your electrode angle is too small. Your arc length is too long. Your welding speed is too slow. Or you're using wet electrodes. All of those are reasons that you can get undercut. Inclusions. Anybody tell me what an inclusion is? Slag inclusion.
Slag trapped in the weld.
Exactly, slag trapped in the weld. That's the most common that you're going to come across. It says entrapped foreign solid materials such as slag, flux, tungsten, or oxide. Tungsten shows up really bright on an X-ray, just white. But those are all different types of tungsten. The ones you're going to be most familiar with will be the slag. Reading from your text now, it says slag inclusions. Slag inclusions, non-metallic particles of slag embedded in the weld, can have a serious adverse effect on the quality of a weld. Usually the slag is from electrode coating, although in some instances particles of slag appear in the base metal and they can be retained in the weld. A lot of times if you're using a cheap steel, there'll be a slag left in that steel from the refining process. It's actually lays in there as a lamination, and you're welding away, and you could suck it into the weld. So you get a discontinuity like that. That's why if you're working to code, you always have to get an MTR, a mill test report, to make sure that the metal that you're using meets quality control standards. Here's a picture of a surface slag inclusion. You can see that big old honking hole right there. Right in here, right in here. And he's got slag trapped all the way along this edge. That's just an ugly weld. This is an X-ray of elongated slag inclusions. These are called wagon tracks. You see this in pipeline welding sometimes, where they've trapped slag on either side of the root bead. And if you look at this X-ray, where it's the darkest, the weld is the thickest. An X-ray works by the X-ray radiation passing through an object, and the more of the X-rays that can get through, the darker it is. So you can see it's darker here, but the less X-rays that can get through, the lighter it remains. And so here you can tell that there's a slag or a void here because there's nothing to stop the X-rays from moving through. Before I go on to porosity, let's see. Just a little bit about slag inclusions. Okay, let's go to porosity on page 215. Porosity, a cavity-type discontinuity formed by gas entrapped during the weld metal solidification. Here's scattered porosity. You can see all those little bubbles. And this is exposed to the surface. Some welding codes will allow no porosity at all exposed to the surface, depending on which code you're working to. Some allow a little bit. This is linear surface porosity with a connecting crack. This was probably done with the gas metal arc process. And what they did here was they probably had their gas flow too small, and so as a result of that, they trapped slag, or pardon me, they got porosity all down through there, and then you subject it to a little bit of stress, and suddenly it cracks. And the crack is going to run from one speck of porosity to the next. This is isolated surface porosity. This is common with the shielded metal arc welding process if it's not used properly. And again, some codes will allow a little bit of that, but most codes won't allow a lot. This is called a wormhole or worm track, elongated surface porosity, where it stretches out like that. That's usually associated with the flux core arc welding process. And this is an X-ray of scattered porosity. Remember, those of you that are into pipe welding, I tell you to stagger your starts and stops. The reason is, if you have some porosity or trap slag or something, and you spread it over a wide distance, it may be acceptable by code. But if you have all your starts and stops in the same spot, it concentrates those discontinuities. And then you might end up with something like this, cluster porosity. Well, that's concentrated in too small an area, so that would not be allowed. See, so you want to stagger your starts and stops, stretch them out, and it could be that same amount of porosity there would be accepted if it was scattered over the entire length of the weld. But since it's concentrated right there, it would not be accepted. So, read page 215 on porosity, and then we'll go over to lack of fusion and incomplete. Well, this is linear porosity. One last photograph here, X-ray. Linear, of course, meaning line. It's a straight line porosity. Incomplete fusion on page 216 now. A weld discontinuity in which fusion did not occur between weld metal and fusion faces or adjoining weld beads. Remember, I've always telling you guys, tie into all the surfaces. Tie into all the surfaces. If you don't, you're going to get incomplete fusion and possible trap slag and such. Reading from your text, it says, lack of fusion and incomplete penetration. Lack of fusion and incomplete penetration are unacceptable in many industrial piping systems, particularly in systems subjected to high pressure. There is such a thing called a partial joint penetration. And there are some designs where you don't have to get complete penetration. But it's got special applications, and it's not usually used in high pressure steam or anything like that. So it's not something that you're likely to run across. If you have incomplete fusion, here's some examples of it. This is a V groove, and it could be pipe or plate. And these are all weld beads that the guys put on here. And you can see a void right here. Well, that's incomplete fusion. Here's another void right here, incomplete fusion. Another void, incomplete fusion. Here's one along the shoulder of the bevel, incomplete fusion. Here, you can see the thickness of the parent metal here, but he didn't tie it in over here, so he has incomplete fusion. Then he has incomplete fusion here on the shoulder of the bevel again. Here he has incomplete root fusion, or incomplete root penetration. All examples of incomplete fusion. Incomplete fusion at the weld face. Essentially, if I see that, the guy didn't complete the weld. He didn't fill it up properly. He didn't break it down properly. That's a defect. If you do that on pipe, they're going to make you fix it. And if you do that more than once, they're probably going to get your money for you. This is incomplete fusion between the weld and base metal. You can see where the metal's just kind of dripped down here a little bit. It's just run into that joint, and incomplete fusion, you can see it started to cause a crack right down here on the root. So this was welded on both sides. But you can see that this edge preparation was only a partial penetration weld preparation, but it's still got to tie in. You can't have that hanging down like that, even on a partial joint penetration. This is an X-ray of incomplete fusion. It's really hard for X-ray to pick up incomplete fusion because it's got to be, the source has to be oriented properly to the fusion, otherwise it's not going to see it. It's too thin. It'd be like trying to X-ray two pieces of paper. If they're laying one on top of the other, you're not going to be able to see that line where the two meet. But if you tip them up on edge and X-ray them, then you're going to see that long through section. And that's the only way you can come up and see that. Incomplete joint penetration. Weld metal does not extend entirely through the joint thickness. The term is used only for groove welds. Here's some examples. This is what I was talking about, a partial joint penetration. That's that picture we were just looking at. And you see, you got to have depth of penetration all the way down in here if you're going to do that. But then this section down here is not completely fused. Here we have incomplete joint penetration at the toe. Here, incomplete joint penetration between these two weldments. And this is much more common. I see this a lot. Incomplete joint penetration at the toe here. Some codes like 1104 will allow a little bit of that. Other codes won't allow any of it. Here's that same photograph again, and also now they've thrown up an X-ray. You can see it's really distinctive, really easy to see on an X-ray if you have incomplete penetration. This is an X-ray of starts and stops. Remember, we call these toenails. It's when you don't have thorough fusion between your tacks and your weld bead. This is very common. I'm sure those of you that are in pipe are very familiar with this. Well, these are defects. They're not allowed. That's a rejection. And when you're out there actually working, if you get more than about a 7% rejection rate, they're not going to retain you. Okay, that's all of my X-ray, or all of my films. Would you turn the light on, please? So, all of these are defects. Certain kinds of defects, different kinds of defects. But by far, that's not all of them. There's a ton more defects. These are just some of the basics. Reading from your text now, how do you repair those? Well, the first step in any repair is to locate the defect and establish its size. Even those defects that are visible to the eye must be evaluated for size in order to avoid excessive removal of the base metal and weld metal. So you're going to look at it. First thing you're going to ask yourself, is it within code? If it's within code, okay, it might be a discontinuity, but it's not necessarily a defect, require repair. If it's outside of code, then it has to be fixed. And most codes require that you have a repair procedure to do that to. Second step, okay, if a welding procedure already exists for the weld being made, then it should be reviewed in terms of the following. the type of material, the electrodes, the joint preparation, interpass temperature, preheating temperature, and you will use the same procedure to make your repair. So how are you going to make that repair? Well, if you turn the page to 218, it says you're going to discern some method for exploring the defect. Determine how you're going to remove the defect. Determine if there's got to be any post-weld heat treatment, what type of electrode you're going to use. You got to make sure you use qualified welders. And if you're using an X-ray, you may do an overlay. You may actually take a little piece of plastic and you put it over your X-ray film and you use a magic marker and you sketch it out. Sketch out that defect. You give it to the welder making the repair. The welder will go out, lay it on, actually on the pipe or wherever, whatever he's working on, and he can see exactly where that defect is, and he can lay it out. And then you just dig right into that spot, and you should be able to find it. Then you're going to make your repair. Once you make your repair, then you're going to have to X-ray it to make sure that it's gotten all out. And you can't be sloppy with it. You've got to be very careful when you're making a repair. First thing you got to do is make sure you get everything out. Make sure you get all the defect out, and then you've got to properly fill it back up again. And if you've got to preheat it, which you probably will have to preheat it, drive all the moisture away from it, make your repair, and then it'll be X-rayed again. Removal of defects. There are two stages of a repair. I'm on page 220 now. It says A, removal of the defects. B, preparation of the defective area for welding. The cavity which has been prepared by gouging or grinding. It says, and now must be dressed by a grinder or a burring tool that can effectively remove the rough surface of the cavity. The repair cavity must be wide enough so that the electrode can fully access the defective area. So you want to make sure you clean everything out. And what's the most important thing in making a repair? Making sure that you get it all out. Making sure that you get it all out. And a lot of times I will ask a welder to get me so I can come and verify that he's got it all removed. Because I deal a lot with X-rays, a lot more than the typical hand does. And so there's such a phenomenon in X-rays called blow-up. And say I wanted to X-ray this cup. Well, if I had my source up here and I shot it, well, then I'd get a nice little flat two-dimensional picture right here. But if I had my source over here and I shot it, now I'm going to get a blown-out picture, just like the sun casting a shadow. And so that may fool a welder into thinking, well, the defect is over here when the defect's actually over here. And so you want to check that to make sure that they've gotten it all out. A weld that is fully prepared should be as follows. The prepared cavity surface must be smooth without peaks and valleys. All traces of oxide must be removed. All spatter and globular deposits in the weld during each welding pass should be removed repeatedly. So you want to make sure you do all of that before you make the final repair. And also, depending on the criticality of it, when we do finally make a repair, we might put the root pass in and then X-ray it or PT it, dye penetrate it to make sure that everything's out. Then we may have to do some additional grinding. And the most important thing is make sure you don't have to go back into it again. I think a typical rule of thumb is you can repair something twice, and the third time you got to cut it out and replace it. So, okay, that's all of chapter 13. Questions? Nope? Okay. Thank you.